What if the fabric of space is not empty at all, but a seething quantum field, filled with energy that we can't see, touch, or directly measure? And what if that hidden energy spread across the cosmos could be tapped into, not by burning fuel or moving mass, but by something far stranger: quantum energy teleportation? For over 2 decades, physicists have grappled with one of the most puzzling discoveries in cosmology. The universe is not just expanding, it's accelerating. Galaxies are drifting apart faster and faster, as though an invisible force is pushing the cosmos outward. Scientists call this phenomenon dark energy, and it accounts for nearly 70% of the entire universe. Yet we still have no clear understanding of what it actually is. At the same time, advances in quantum theory have revealed that energy can, in principle, be transmitted across space without any particles traveling between 2 points. This process, quantum energy teleportation, relies on entanglement, measurement, and local operations. It doesn't violate relativity or conservation laws, but it does challenge our deepest intuitions about how energy moves. Could these two mysteries be connected? Could the accelerating expansion of the universe, driven by dark energy, be explained by some form of quantum energy transfer happening on cosmic scales? Tonight, we will follow the science behind that question, from the foundations of quantum theory to the paradoxes of vacuum energy, from groundbreaking experiments to bold theoretical proposals. In the early decades of the 20th century, astronomers believed the universe was static, unchanging on the grandest scales. Even Albert Einstein, whose equations of general relativity implied a dynamic universe, introduced a term he called the cosmological constant to force his model to stay still. He later called it his biggest blunder. But everything changed in the 1920s. Edwin Hubble, using the 100-inch Hooker telescope at Mount Wilson Observatory in California, observed that distant galaxies appeared to be moving away from us. The farther away a galaxy was, the faster it seemed to recede. This observation gave rise to the concept of an expanding universe, a universe that was once smaller, denser, and hotter. This idea soon became the foundation of modern cosmology. For much of the 20th century, the scientific consensus held that although the universe was expanding, gravity would gradually slow this expansion over time. Perhaps, depending on how much mass the universe contained, the expansion would eventually reverse, causing a collapse, or perhaps it would slow indefinitely, approaching a halt. Either way, most scientists expected that gravity, acting across billions of galaxies, would act as a cosmic brake. But in the late 1990s, 2 independent teams of astronomers made a startling discovery. By observing a special type of exploding star known as a Type Ia supernova, they could measure both the distance to the supernova and the speed at which its host galaxy was receding. These supernovae act like cosmic mileposts, predictable in brightness and relatively easy to spot across vast distances. The teams, one led by Saul Perlmutter at the Lawrence Berkeley National Laboratory and another led by Brian Schmidt and Adam Rees, began comparing the observed brightness of these supernovae to what they expected. What they found shocked them. The supernovae were dimmer than expected, which meant they were farther away than the standard models predicted. The implication: the universe was not slowing down, it was speeding up. In 1998, both teams published their findings. The expansion of the universe, instead of decelerating, was accelerating. Something was overcoming the attractive pull of gravity, something unseen, unaccounted for, and dominating the dynamics of the cosmos. This unknown influence became known as dark energy. To be clear, the term dark energy does not refer to a specific substance. It's a placeholder, a name for whatever it is that's causing the expansion of the universe to accelerate. It does not glow, reflect light, or interact with matter in any way that we can currently measure directly. It is dark, not only in visibility, but in understanding. To explain the accelerating universe, cosmologists reintroduced Einstein's discarded cosmological constant, the Greek letter lambda. In the equations of general relativity, this constant acts like a pressure intrinsic to space itself, a kind of vacuum energy that doesn't dilute as the universe expands. In fact, the more space you have, the more total energy is associated with it. This fits the data surprisingly well. If the universe is filled with a constant vacuum energy density, then as the universe expands, more space means more of this repulsive pressure. The acceleration is built into the mathematics, and this cosmological constant model remains the simplest explanation for dark energy. However, a major problem arises when we ask, where does this vacuum energy come from? Quantum field theory, our best theory of particles and forces, predicts that even in a perfect vacuum, fields are never truly zero. They fluctuate constantly due to the uncertainty principle. These fluctuations mean that even empty space contains energy, the so-called zero-point energy of the vacuum. When theorists try to calculate how much energy should exist in a cubic centimeter of empty space, the numbers are staggering. Depending on the details of the calculation, the predicted vacuum energy density is about 120 orders of magnitude larger than what is inferred from cosmological observations. This discrepancy between theory and measurement is often cited as the worst prediction in the history of physics. Despite this, the cosmological constant remains the leading model for dark energy because it matches what we see. Galaxies moving apart faster over time, the expansion accelerating in a way that fits with a constant vacuum energy density. Observations of the cosmic microwave background radiation, galaxy clustering, and baryon acoustic oscillations all support this model. To quantify dark energy's dominance, scientists often refer to the energy budget of the universe. According to measurements from the Planck satellite and other observatories, about 68% of the universe consists of dark energy. Dark matter, another invisible, poorly understood component, accounts for about 27%. Ordinary matter, the stuff that makes up atoms, stars, and people, contributes only about 5%. That means everything we've ever observed directly, galaxies, gas clouds, planets, even light, is just a thin layer atop a much deeper and stranger cosmic reality. The majority of the universe is composed of things we do not understand. Over the past 2 decades, scientists have proposed various alternatives to the cosmological constant. Some involve dynamic fields, such as quintessence, which could evolve over time and space. Others invoke modifications to gravity itself at large scales. Still others consider extra dimensions or emergent spacetime models, but none of these alternatives has matched the simplicity and observational success of the cosmological constant. Still, the mystery remains. What is the nature of dark energy? Why is the energy density of the vacuum so small, yet not zero? And why did the effects of dark energy become dominant only recently in the history of the universe, billions of years after the Big Bang? These are not just academic questions. Understanding dark energy means understanding the fate of the universe. If dark energy remains constant, the cosmos will continue expanding forever, becoming colder, emptier, and more diffuse, a future sometimes called the heat death of the universe. If it evolves, or if its properties change, the story could be very different. The universe might tear apart in a violent Big Rip, or slow down again in ways we cannot yet foresee. The stakes are immense, and the challenge is formidable. To solve the mystery of dark energy, we may need more than better telescopes. We may need new physics. To understand how dark energy might connect to quantum theory, we must first look more closely at the strange foundational world that quantum physics describes. A world where energy, space, and even information behave in ways that defy classical logic. It is here, in the early history of quantum mechanics, that we find the principles that would eventually challenge our notions of what energy is, how it moves, and whether it might be transferred in ways stranger than we ever imagined. At the beginning of the 20th century, physics stood on seemingly solid ground. Newtonian mechanics explained motion and force. Maxwell's equations unified electricity and magnetism. Thermodynamics defined heat and entropy. The world appeared rational, predictable, and governed by universal laws. Yet a few experimental results began to expose cracks in that classical framework. One of the earliest signs came from the study of blackbody radiation, the light emitted by heated objects. According to classical physics, a blackbody should emit increasing amounts of energy at shorter wavelengths, leading to what became known as the ultraviolet catastrophe. But in 1900, Max Planck introduced a radical idea to fix the problem. He proposed that electromagnetic energy could only be emitted or absorbed in discrete units, which he called quanta. These energy packets were proportional to the frequency of radiation, with the now famous relation: energy equals Planck's constant multiplied by frequency, Planck did not initially believe that energy was truly quantized. He treated the idea as a mathematical trick, but a few years later, Albert Einstein took it seriously. In 1905, Einstein applied the quantum idea to explain the photoelectric effect, the observation that light could knock electrons off a metal surface, but only if the light's frequency was above a certain threshold, regardless of its intensity. Einstein argued that light itself must come in discrete particles, later called photons. For this work, he was awarded the Nobel Prize in Physics in 1921. This idea, that light behaves not only as a wave but also as a particle, was revolutionary. It suggested that the classical wave theory of light was incomplete and that energy in nature was fundamentally granular. Soon after, experiments with electrons and atoms revealed even stranger behavior. Electrons appeared to interfere with themselves, as if they were both waves and particles. Niels Bohr developed the first quantum model of the hydrogen atom, proposing that electrons orbited the nucleus in fixed energy levels and could jump between them by absorbing or emitting photons. The model was successful, but it lacked a deeper explanation. By the 1920s, a new generation of physicists took quantum theory further. Werner Heisenberg formulated matrix mechanics, while Erwin Schrödinger developed wave mechanics. Schrödinger's famous equation described how the wave function of a quantum system evolves over time. The wave function itself represented a probability distribution, not a physical object, but a mathematical tool for predicting outcomes. This was a major shift from classical physics, which had always described specific properties like position and velocity. At the core of quantum mechanics lies a profound principle: uncertainty. Heisenberg's uncertainty principle states that certain pairs of physical properties, such as position and momentum, cannot both be precisely known at the same time. The more accurately one is known, the less precisely the other can be determined. This is not due to limitations in measurement tools, but a fundamental aspect of nature. Another key development was the principle of superposition. In quantum systems, particles do not exist in one definite state until measured. Instead, they exist in a superposition of all possible states. When a measurement occurs, the system appears to collapse into a definite outcome. This led to heated debates among physicists about the meaning of measurement and the nature of reality. Albert Einstein, despite his foundational contributions, was deeply skeptical of the probabilistic nature of quantum mechanics. He famously remarked, "God does not play dice with the universe." In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a thought experiment known as the EPR paradox. They argued that quantum mechanics must be incomplete because it allowed for what they called spooky action at a distance, correlations between particles separated by vast distances. This spooky action would later be recognized as quantum entanglement. When two particles become entangled, the measurement of one immediately determines the state of the other, no matter how far apart they are. Yet no information travels between them faster than light. The effect is instantaneous but does not violate relativity because it cannot be used to send messages. The EPR paper challenged the completeness of quantum mechanics, but in doing so, it set the stage for one of the most important developments in modern physics. In the 1960s, physicist John Bell formulated what became known as Bell's theorem. He showed that no theory based on local hidden variables, that is, a theory where properties exist independently and are influenced only by their immediate surroundings, could reproduce all the predictions of quantum mechanics. Experiments testing Bell's inequalities began in the 1970s and culminated in the 1980s with Alain Aspect's pioneering work in France. Aspect's experiments demonstrated that the correlations between entangled particles violate Bell's inequalities, confirming the predictions of quantum mechanics. The results strongly suggest that either reality is non-local, allowing influences across space, or that our classical understanding of reality is deeply flawed. Today, quantum mechanics is the most precisely tested theory in physics. It forms the basis for modern technologies including semiconductors, lasers, magnetic resonance imaging, and emerging quantum computers. Yet despite its practical success, its interpretation remains one of the deepest philosophical puzzles in science. For our purposes, several features of quantum mechanics are especially relevant. The existence of vacuum fluctuations, the idea that particles can be entangled across space, and the role of information in quantum systems. Together, these features hint at the possibility that energy might not be as localized as we once thought, and that under certain conditions, it could be accessed or transferred without conventional movement. Quantum mechanics does not merely describe particles bouncing around. It describes a universe where the void is alive with uncertainty, where measurement changes outcomes, and where entanglement defies distance. In this framework, even the concept of energy must be reconsidered. It is no longer just kinetic motion or potential stored in a field. It is also linked to probability, to the collapse of wave functions, and to the structure of information itself. To truly grasp how quantum mechanics might help explain dark energy, we need to move beyond particles and begin thinking in terms of fields, continuous entities that fill all of space, even in the absence of matter. These fields are not just mathematical abstractions. They are the foundation of modern physics, and they change how we think about energy, space, and the vacuum itself. At the heart of this understanding lies quantum field theory, often abbreviated as QFT. This framework combines quantum mechanics with special relativity and forms the backbone of the standard model of particle physics. In this picture, every particle is an excitation of an underlying field. Electrons, for example, are ripples in the electron field. Photons are ripples in the electromagnetic field. What we perceive as solid matter is, at a deeper level, the interaction of vibrating quantum fields. In classical physics, a field might seem simple. The temperature at every point in a room is a kind of field, a number assigned to each location in space. A magnetic field assigns direction and strength to each point in a region. But in quantum field theory, fields are much more dynamic and strange. They fluctuate constantly, even in what we call a vacuum. The quantum vacuum is not a calm, empty void. It is a restless sea of uncertainty. According to the Heisenberg uncertainty principle, we cannot simultaneously know a field's value and how quickly it's changing. As a result, quantum fields are never truly at rest. Even in the lowest energy state, the vacuum, they experience continuous fluctuations. These fluctuations are not just theoretical. Their effects have been measured in experiments. One of the most famous examples is the Casimir effect, named after Dutch physicist Hendrik Casimir. In 1948, Casimir predicted that if two uncharged parallel metal plates are placed extremely close together in a vacuum, they would experience a tiny attractive force. This force does not come from any classical interaction, but from a difference in vacuum energy between the inside and outside of the plates. The quantum field modes that fit between the plates are restricted, while outside the plates, all modes are allowed. This imbalance produces a measurable force, one that has been confirmed in laboratory experiments with remarkable precision. Another consequence of quantum vacuum fluctuations is seen in what's called Lamb shift, a small difference in energy levels of the hydrogen atom, first measured by Willis Lamb in the 1940s. This shift arises due to interactions with the fluctuating electromagnetic vacuum, further supporting the idea that even empty space is teeming with activity. So if vacuum fluctuations are real, and if they carry energy, then how much energy does the vacuum contain? This question has led to one of the most astonishing and troubling results in theoretical physics. When physicists attempt to calculate the energy density of the vacuum by summing up the contributions from all possible quantum field modes, the result is enormous. Theoretically, the vacuum should contain an energy density that is many orders of magnitude higher than what we observe in the cosmos. Some estimates suggest that the predicted value is about 10 raised to the power of 120 times greater than the observed value of dark energy. This mismatch is what physicists refer to as the vacuum catastrophe. It is not simply a small error, it is the largest known discrepancy between theory and observation in the history of science. Something fundamental is missing in our understanding. One might ask, if vacuum energy is so enormous, why doesn't it curve spacetime to a much greater degree? After all, in Einstein's general relativity, energy and mass determine the curvature of spacetime. If vacuum fluctuations contribute real energy, then that energy should gravitate. It should produce a cosmological constant far larger than what is compatible with the structure and history of our universe. Physicists have proposed various mechanisms to cancel or suppress the vacuum energy. Some involve symmetries that force the total energy to zero. Others suggest that some yet unknown dynamics in quantum gravity might regulate the vacuum. But so far, none of these solutions has been fully successful or experimentally confirmed. This leads to a fascinating possibility. Perhaps vacuum energy is not a constant at all. Perhaps it can be accessed, manipulated, or redistributed under certain conditions. And perhaps the quantum fields that pervade all space hold the key. In the language of quantum field theory, energy is not just a global quantity. It can be defined locally, depending on how fields are configured in a particular region. In fact, under certain circumstances, it is possible to create regions of negative energy density where the energy is lower than the vacuum level. This is permitted in quantum theory as long as the total energy, integrated over all space and time, remains positive. These strange energy distributions are not just theoretical curiosities. They appear in discussions of exotic phenomena such as the Hawking radiation from black holes or the hypothetical construction of wormholes and warp drives. But they also appear in more grounded proposals, such as quantum energy teleportation, an idea that we will explore in depth later in this documentary. The key insight is this: in a quantum field, measurement itself can change the energy configuration of space. When we interact with a quantum system, even passively, by making a measurement, we alter its state. That change has energetic consequences. In certain setups, it is possible to lower the energy in one region and raise it in another through processes that involve entanglement and information transfer. This is radically different from classical ideas of energy transmission. In the classical world, energy is transmitted by moving something, a wave, a particle, a fluid, or a field. But in quantum field theory, energy can be reallocated through correlations even when no physical substance moves from point A to point B. That does not violate conservation laws or causality, but it challenges our intuition. To prepare for this, we must become comfortable with the idea that the vacuum is not empty. It is the ground state of all quantum fields, filled with zero-point energy and fluctuations. This background activity is not an artifact of our measurements. It is a fundamental part of the universe. Moreover, the vacuum is not uniform. Depending on how we look at it, and depending on the presence of observers or horizons, what counts as vacuum may differ. This is seen in the Unruh effect, where an accelerating observer perceives a warm bath of particles in what an inertial observer sees as empty space. Similarly, the presence of a black hole's event horizon changes the vacuum state, leading to the emission of Hawking radiation. These phenomena suggest that vacuum energy is not a fixed, immutable quantity. It is a dynamic aspect of spacetime and fields, sensitive to context, observer, and interaction. As we seek to understand the origin of dark energy, this realization becomes crucial. Perhaps the small but non-zero cosmological constant we observe is not a mistake in calculation, but the result of an averaging process, a residual from deeper quantum dynamics. Or perhaps, under the right conditions, the vacuum can be used, not only to explain cosmic expansion, but to transmit energy across space. To understand how the concept of vacuum energy became part of modern cosmology, we must return to the early days of general relativity, and to Albert Einstein himself. It was Einstein's groundbreaking insight that gravity is not a force transmitted through space, but a feature of space and time themselves. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. This elegant formulation became the basis of general relativity, completed in the year 1915. Shortly after publishing his field equations, Einstein began applying them to the universe as a whole. At the time, the prevailing belief, supported by philosophical assumptions rather than data, was that the universe was static and eternal. But when Einstein inserted his equations into a cosmological model, he found that gravity would inevitably cause the universe to either collapse inward or expand outward. A static solution did not naturally arise. To counteract this, Einstein introduced an additional term to his equations. He called it the cosmological constant, denoted by the Greek letter lambda. This term acted as a repulsive force, a uniform energy density filling space, which could balance the attractive pull of gravity and allow the universe to remain static. Einstein did not consider lambda to represent a physical substance. Instead, it was a mathematical fix, inserted for the sake of matching what he and others believed the universe ought to be. This adjustment satisfied the desire for a steady-state cosmos, but it also raised philosophical discomfort. Why should there be a perfectly balanced universe, poised between expansion and collapse? Was this balance stable? Could the tiniest fluctuation cause the cosmos to drift into motion? In the years that followed, Einstein's cosmological constant sat uneasily within theoretical physics. It made the equations work, but its justification was weak. Then, in the 1920s, astronomical observations began to shift the picture. Edwin Hubble's work at Mount Wilson Observatory revealed that galaxies are not stationary. They are receding from one another, and the farther away they are, the faster they recede. The universe, it turned out, was not static at all. It was expanding. This revelation made Einstein's cosmological constant unnecessary. If the universe is in motion, there is no need for a special term to hold it still. Einstein reportedly referred to lambda as the biggest blunder of his life, though historical evidence suggests this quote may be apocryphal. Regardless, the scientific community largely abandoned the cosmological constant for much of the 20th century. In the following decades, cosmologists developed dynamic models of the universe, models that incorporated the expansion observed by Hubble and others. The standard model of cosmology emerged, describing a universe that began in a hot, dense state and evolved over billions of years. Matter, radiation, and dark matter shaped the structure of galaxies and clusters. Lambda was no longer part of the discussion. But in the final years of the 20th century, something unexpected happened. As covered in our earlier section, teams of astronomers studying distant type Ia supernovae found that the expansion of the universe was not slowing down. It was accelerating. To explain this, the cosmological constant was resurrected, no longer as a mathematical convenience, but as a physical reality. In modern cosmology, lambda is understood as a form of vacuum energy, an intrinsic energy density of space itself. Unlike matter or radiation, which dilute as the universe expands, this energy remains constant per unit volume. As space grows, so does the total amount of this energy. The effect is a steady, repulsive push that becomes dominant once the universe is large and dilute enough. Lambda is now a central parameter in what is known as the lambda-cold dark matter model, or lambda CDM. This model successfully explains a wide range of cosmological observations, from the distribution of galaxies to the fluctuations in the cosmic microwave background radiation. In this framework, the cosmological constant accounts for the phenomenon we call dark energy. However, this new physical interpretation of lambda comes with major theoretical challenges. One of the most persistent issues is its size. When derived from quantum field theory, the expected vacuum energy is vastly larger than what lambda appears to be. As discussed in the previous section, the discrepancy between prediction and observation is staggeringly large, by about 1 part in 10 raised to the 120th power. This suggests that something deep is missing in our theories. Either there is a cancellation mechanism that reduces vacuum energy to the tiny level we observe, or our understanding of gravity, quantum fields, or both, needs revision. Some physicists speculate that the observed value of lambda may be the result of anthropic selection, the idea that only in a universe with such a small value could observers like us exist. Others seek dynamical explanations involving scalar fields or modifications to general relativity. Yet for all its mystery, lambda remains the simplest and most effective way to model dark energy. It has no dynamics, no direction, and no evolution. It is simply there, an ever-present pressure that shapes the fate of the cosmos. One way to interpret lambda is as a kind of tension in the vacuum, a stretching of space-time that acts equally in all directions. This tension does not clump, collapse, or flow. It acts as a background to everything else, setting the large-scale behavior of the universe. Because it is uniform, it does not interfere with local structures like galaxies, stars, or planets. Its effects only become visible on cosmological scales. The fact that lambda was first introduced for one reason, discarded for another, and later revived for a third, is a striking example of how science evolves. Ideas are not fixed in stone. They are tools that gain or lose value depending on how well they match observations. In this case, Einstein's original term has become the leading explanation for a cosmic mystery he never anticipated. But the story does not end there. In recent years, new theoretical developments have emerged that connect lambda, vacuum energy, and quantum information. Some physicists have begun exploring whether the structure of space-time itself might emerge from quantum entanglement. Others have proposed mechanisms by which energy could be redistributed across space through quantum processes, potentially offering a new way to understand dark energy. This brings us directly into one of the most persistent and perplexing conflicts in theoretical physics, a clash between quantum field theory and general relativity that culminates in what physicists call the vacuum catastrophe. At its heart lies a seemingly simple question: how much energy is there in empty space? As we have already seen, quantum field theory paints a very different picture of the vacuum than classical physics. In the quantum realm, even empty space is alive with fluctuations, spontaneous appearances and disappearances of virtual particles, constant jittering of fields, and uncertainty in every direction. These fluctuations do not require any external input. They arise naturally from the principles of quantum mechanics. According to the uncertainty principle, if you try to define the energy of a system with infinite precision over zero time, you will get an infinite result. This principle means that even in a vacuum, a space devoid of particles, energy still resides. Physicists call this the zero-point energy of the vacuum. It is the lowest possible energy state of a quantum field, but it is not zero. And since space is filled with quantum fields, the vacuum itself should possess an enormous amount of energy. So how much energy are we talking about? To answer that, theoretical physicists began estimating the vacuum energy density using the tools of quantum field theory. These calculations involve summing the contributions of all possible quantum fluctuations across all modes and frequencies in all the known fields. And this is where the problem arises. The number that emerges from this procedure is staggering. Depending on the cutoff chosen, that is, the maximum frequency allowed in the summation, the calculated vacuum energy density can be over 100 orders of magnitude larger than what is observed cosmologically. In the most straightforward version of the calculation, the discrepancy is about 10 raised to the 120th power. This is not just a large number, it is the largest known disagreement between theory and experiment in the history of science. To put it in perspective, imagine calculating the weight of the Earth and getting a number larger than the mass of the entire observable universe. That is the scale of error we are dealing with. This monumental mismatch is what physicists refer to as the vacuum catastrophe, a dramatic failure to reconcile two of the most successful theories ever developed: general relativity, which governs gravity and the large-scale structure of the cosmos, and quantum field theory, which governs particles, forces, and the microscopic world. In principle, the vacuum energy should act as a source of gravity, curving space-time and affecting the expansion of the universe. This is exactly what the cosmological constant does in Einstein's equations. But if we took the quantum predictions at face value, the universe should be expanding at a rate so fast that no structure, no galaxies, no stars, no planets could possibly form. But that is not what we observe. The real universe, as measured by observations of supernovae, the cosmic microwave background, and the large-scale distribution of galaxies, shows a much gentler acceleration. The inferred vacuum energy is incredibly small, yet it is not zero. That is the puzzle. Why is the vacuum energy so small, and why is it not exactly zero? This problem has attracted some of the greatest minds in physics over the past several decades. Steven Weinberg, who played a key role in unifying the weak nuclear force with electromagnetism, proposed one of the earliest anthropic arguments related to this issue. In the 1980s, Weinberg suggested that if the vacuum energy were significantly larger than it is, either positive or negative, galaxies could not form. In such a universe, no observers like us could exist to measure it. This line of reasoning led to the idea that perhaps the vacuum energy is not fixed by a fundamental law, but varies across different regions of a much larger multiverse. In this view, we happen to live in a region where the vacuum energy is small enough to allow complex structures and life. While this proposal is logically consistent, it remains controversial, largely because it is difficult, if not impossible, to to test or falsify. Many physicists prefer to search for a more predictive and dynamical explanation. Another line of investigation involves the possibility that some unknown symmetry or cancellation mechanism reduces the vacuum energy to nearly zero. Supersymmetry, a proposed extension of the Standard Model, originally offered hope in this direction. In a perfectly supersymmetric world, every particle has a superpartner with identical mass but different spin. The vacuum energy contributions from bosons and fermions would exactly cancel out. Unfortunately, we do not live in a perfectly supersymmetric world. No superpartners have been detected, and if supersymmetry exists, it must be broken at energy scales far above those we have probed so far. This breaking reintroduces the vacuum energy, leaving the problem unresolved. Others have suggested that the cosmological constant is not constant at all. Perhaps it is the result of a slowly evolving field, a new form of energy known as quintessence. In these models, the vacuum energy changes over time, influenced by the dynamics of an unknown scalar field. Unlike the cosmological constant, which remains fixed, quintessence evolves and might eventually decay or change its influence on the expansion of the universe. Although appealing in some ways, these models require fine-tuning and have yet to produce definitive observational signatures. More speculative proposals come from approaches to quantum gravity, such as string theory or loop quantum gravity. In some versions of string theory, the vacuum energy is determined by the shape and size of extra dimensions curled up at microscopic scales. These dimensions might allow for a vast landscape of possible vacuum states, a feature sometimes called the string landscape. However, navigating this landscape and finding the right vacuum state that matches our universe remains a daunting challenge. Meanwhile, approaches such as emergent gravity or holographic theories suggest that spacetime and gravity themselves might arise from deeper quantum information principles. In such views, the vacuum energy could be an emergent property, not a fundamental input. These are still developing ideas, but they offer the tantalizing hope of reconciling quantum theory with gravity in a way that explains the smallness of the cosmological constant. Despite decades of effort, no universally accepted solution to the vacuum catastrophe has emerged. It remains one of the most profound unsolved problems in physics. But within this frustration lies opportunity. The very severity of the mismatch forces us to question assumptions, to explore new frameworks, and to rethink the nature of space, time, and energy. And this is where a surprising idea begins to take shape. An idea rooted not in new particles or extra dimensions, but in the informational structure of quantum systems. It suggests that energy might be extractable from the vacuum using measurements, and that the vacuum's properties might be more malleable than we imagined. This idea is called quantum energy teleportation. Before energy can be manipulated or even remotely accessed in the quantum world, something more fundamental must be in place. A connection, invisible yet measurable, known as quantum entanglement. This peculiar feature of quantum systems is not just a curiosity. It is a foundational part of how nature works at the deepest level, and it may be the key to understanding how processes like quantum energy teleportation and possibly even dark energy function across vast cosmic distances. Entanglement is the phenomenon where two or more quantum systems become correlated in such a way that the state of one cannot be fully described without considering the state of the other, no matter how far apart they are. When particles are entangled, measurements performed on one immediately affect the outcome of measurements on the other. This is true even when the particles are separated by distances that would normally preclude any classical influence. To understand how this works, it helps to trace the history of the concept. In the year 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper that challenged the completeness of quantum mechanics. In it, they proposed what is now known as the EPR paradox. Their argument centered on the idea that if quantum mechanics were complete, then it must allow for what they called spooky action at a distance, a seemingly instantaneous influence between entangled particles. Einstein and his colleagues found this deeply troubling. They believed that any real theory of physics should be local, meaning that effects should only be caused by nearby interactions. The idea that a measurement on one particle could instantly affect another, located far away, seemed to violate both causality and the speed limit set by the speed of light. The EPR paper posed a challenge, but it did not disprove quantum mechanics. Instead, it set the stage for further investigation. In the year 1964, physicist John Bell developed a mathematical framework that allowed the EPR paradox to be tested experimentally. Bell's theorem showed that if the world were governed by local hidden variables, predetermined properties that exist independently of observation, then certain statistical correlations between entangled particles should obey specific inequalities. But quantum mechanics predicted that these inequalities could be violated. If experiments confirmed the violation, it would mean that no local hidden variable theory could fully explain quantum behavior. Beginning in the 1970s and continuing into the 1980s, a series of increasingly precise experiments were carried out, most notably by Alain Aspect and his team in France. They studied the correlations between the polarizations of entangled photons and found results in clear violation of Bell's inequalities. These experiments strongly supported the quantum view: entangled particles do not behave according to local realism. Instead, they exhibit correlations that seem to transcend space. Since then, entanglement has been confirmed in many different physical systems, including electrons, ions, and even small molecules. It has become one of the most tested and validated predictions of quantum theory. But what does this have to do with energy? In classical physics, energy and information are distinct entities. You can send a signal without transferring energy, and you can transfer energy without encoding information. But in quantum theory, the two are more deeply connected. Measurement itself changes the energy of a quantum system, and in entangled systems, the information gained from one part can be used to influence or extract energy from another, even when the systems are spatially separated. This leads to a remarkable possibility. If two regions of space share entanglement, then operations performed in one region, combined with classical communication, might allow energy to be extracted from the vacuum in the other. This idea lies at the heart of quantum energy teleportation, which we will explore in greater detail soon. But the entire mechanism depends on one prerequisite: pre-existing entanglement. So how far does entanglement extend? In a laboratory, entangled particles can be created in pairs and sent in opposite directions. Experiments have shown entanglement persisting over distances of hundreds of kilometers. In recent years, satellites have been used to demonstrate entanglement distribution between ground stations separated by thousands of kilometers. The Chinese satellite Mikius, launched in the year 2016, successfully performed quantum key distribution using entangled photons, proving that entanglement can be maintained over vast distances, even through the noisy environment of Earth's atmosphere. But these engineered systems are relatively simple. The more profound question is whether entanglement exists naturally, on much larger scales. Could the universe itself be entangled? Some physicists believe the answer may be yes. In quantum field theory, the vacuum is not just a passive background, it is a highly entangled state. Even regions of empty space that are far apart can exhibit quantum correlations. This is not the result of any particular particles being entangled, but rather a feature of the field itself. The entanglement is distributed continuously throughout space, embedded in the structure of the vacuum. This idea is supported by studies in quantum information theory, particularly in the concept of entanglement entropy. Entanglement entropy measures how much information is shared between different parts of a quantum system. In many field theories, the entanglement entropy between a region and its complement scales with the area of the boundary between them, not the volume. This so-called area law hints at a deep connection between geometry and quantum information. Further support comes from studies in black hole physics. The Bekenstein-Hawking formula, which relates the entropy of a black hole to the area of its event horizon, suggests that information and geometry are intimately related. More recently, researchers such as Juan Maldacena and Mark van Ramsdonk have explored how entanglement might be responsible for the emergence of spacetime itself. In some models, the connectivity of spacetime is literally built from patterns of entanglement in the underlying quantum fields. One particularly influential idea is the ER-EPR conjecture, proposed by Leonard Susskind and Juan Maldacena. This conjecture suggests that Einstein-Rosen bridges, better known as wormholes, might be equivalent to entangled particle pairs. If true, it would imply that entanglement and geometry are two sides of the same coin. Although these ideas remain speculative, they point to an astonishing possibility. That entanglement may not be a local, isolated phenomenon, but a global feature of the universe. If so, then distant regions of space might already share entanglement. And if that entanglement can be harnessed, it might allow for processes that redistribute energy, not by sending particles through space, but by using information, measurement, and local operations. This is not a violation of causality or energy conservation. In all such processes, classical information must still be transmitted, bound by the speed of light, and the total energy remains conserved. But the mechanism of transfer is unlike anything in classical physics. It does not involve sending energy through a medium. It involves reconfiguring the vacuum itself, using correlations that already exist. Understanding this requires a shift in perspective. In the quantum world, the vacuum is not an absence. It is a resource, rich in structure and potential. It can be probed, perturbed, and under the right conditions, tapped. This is the conceptual foundation upon which quantum energy teleportation is built. It requires shared entanglement, precise measurement, and controlled operations. And while it may sound like science fiction, the idea is grounded in rigorous mathematics and has been explored by theoretical physicists over the past 2 decades. The first step toward formalizing this concept came from a single physicist in Japan who published a bold new idea in the year 2008, an idea that took entanglement and measurement into a new realm, not just for transferring information, but for relocating energy. To understand how quantum energy teleportation could actually work, we need to examine the surprising relationship between information and energy, a connection that is far more than metaphorical. In classical physics, energy and information belong to separate domains, one physical, one abstract. But in the quantum world, and especially in the realm of thermodynamics, the two are intertwined. This connection is captured most clearly by a foundational insight from the mid-20th century, known as Landauer's principle. The principle is named after Rolf Landauer, a physicist working at IBM in the early 1960s. At the time, computing technology was advancing rapidly, and researchers were becoming increasingly interested in the physical limits of computation. What was the minimum amount of energy required to perform a logical operation? Could computers operate without dissipating heat? Landauer's contribution was subtle but profound. He recognized that the act of erasing information, not merely processing or storing it, had an unavoidable thermodynamic cost. Specifically, he showed that erasing a single bit of information must generate a minimum amount of heat, proportional to the ambient temperature, and a universal constant. This insight linked computation directly to the second law of thermodynamics. The second law, as commonly understood, states that the entropy of a closed system tends to increase over time. Entropy can be interpreted in many ways, as disorder, uncertainty, or the number of microstates compatible with a given macrostate. In Landauer's framework, information is a form of negative entropy. To erase it is to increase entropy, and that increase requires energy. This principle may sound abstract, but it has very real consequences. It sets a physical limit on how efficient computers can be. More importantly for our purposes, it establishes a fundamental equivalence between information and energy. Not all information has energy, but some information, when manipulated or discarded, necessarily involves an energy transaction. To erase one bit of information at room temperature requires a minimum of about 3 × 10 to the negative 21st joules of energy. That is an unimaginably small quantity, but it is not zero. And when you consider the trillions of operations performed by modern processors, the total energy cost becomes significant. Today's most advanced microchips must manage heat dissipation carefully because logical operations generate real physical heat. Landauer's principle was not merely a technical observation. It helped resolve a long-standing paradox in physics, the so-called Maxwell's demon thought experiment. In the 19th century, James Clerk Maxwell imagined a tiny demon capable of sorting fast and slow gas molecules without expending energy, seemingly violating the second law of thermodynamics. For decades, this idea puzzled scientists. If the demon could extract useful work by creating a temperature difference, where did the entropy go? Landauer's insight provided the answer. The demon could gather information, yes, but at some point, it would need to erase memory to make room for more. That erasure would generate entropy, restoring the balance. The second law was safe, but only because information processing had been recognized as a physical process with energetic consequences. This deepened the connection between information theory and physics. Later work by Charles Bennett, also at IBM, extended these ideas further. Bennett showed that certain logical operations could, in principle, be performed reversibly without energy dissipation, as long as no information was erased. But once erasure or copying occurred, thermodynamic costs returned. Why does this matter in the context of quantum energy teleportation? Because any protocol that extracts or redistributes energy based on measurements must involve information. In quantum mechanics, a measurement is not passive. It changes the state of the system. When a measurement is made on a quantum field, even in the vacuum state, it injects energy into the system. The act of acquiring knowledge has physical consequences. In the case of quantum energy teleportation, which we will explore in the next section, the protocol begins with a measurement in one location, a local probe of the quantum field. That measurement disturbs the vacuum and yields some classical information. That information is then transmitted via ordinary communication channels to a distant location. At that second location, a conditional operation is performed based on the received information. The result is the extraction of energy from the vacuum, even though no particle or wave traveled between the 2 points. At first glance, this might appear to violate conservation of energy. How can energy be extracted from a distant location without sending anything there? But when analyzed carefully, the total energy remains conserved. The initial measurement injects energy into the field. The second operation allows energy to be extracted, but only if the proper correlations, created by entanglement, already exist. And crucially, classical information must be transmitted between the sites. No faster than light signaling is possible. The key is that the measurement and the subsequent operation are not independent. They are linked by shared quantum correlations and classical information flow. In a very real sense, energy is not moving through space. It is being relocated through the manipulation of information. Landauer's principle gives us the intellectual tools to understand how this is possible. If erasing a bit requires energy, then extracting energy must also involve the creation or exploitation of information. The quantum vacuum is not an empty reservoir. It is an entangled system filled with latent correlations that can be tapped, but only by paying the price in information. This changes how we think about the vacuum. It is not merely a low-energy state, but a structured resource. Measurement accesses that structure, revealing correlations that can be used to perform work. In this way, energy becomes less of a substance and more of a potential that can be activated through knowledge. Physicist Masahiro Hotta, whom we will discuss in the next section, drew directly on these principles when formulating his theory of quantum energy teleportation. His insight was that by combining entanglement, measurement, and classical communication, one could relocate energy in a controlled and theoretically lawful way. Nothing is sent faster than light, nothing is created from nothing, and yet energy is redistributed across space. This idea would not be credible without the foundational work of Landauer and Bennett, who revealed the thermodynamic cost of information processing. Their insights laid the groundwork for a new understanding of how information, energy, and entropy are fundamentally connected. Building upon the deep relationship between information and energy and rooted in the entangled structure of the quantum vacuum, a bold new proposal emerged in the early 21st century, one that pushed the boundaries of how energy might be transmitted through space. In the year 2008, Japanese physicist Masahiro Hotta introduced the concept of quantum energy teleportation, or QET, in a formal scientific paper. His idea drew from the principles we have been carefully assembling: quantum entanglement, vacuum fluctuations, measurement-induced energy changes, and Landauer's thermodynamic framework. But what exactly is quantum energy teleportation? In its most basic formulation, QET is a theoretical protocol that allows energy to be extracted from a distant region of space without any physical substance. No particles or radiation traveling between the 2 points. This sounds impossible at first glance, but it is not. It does not violate conservation of energy, causality, or any known law of physics. Instead, it relies on the subtleties of quantum field theory and the pre-existing entanglement of the vacuum state. To appreciate how QET works, it helps to think in terms of three key components: local measurement, classical communication, and conditional local operation. These steps form the backbone of the protocol and ensure that all physical laws remain intact. The process begins with a measurement performed on a quantum field at a specific location, which we can call point A. This measurement is typically local, meaning it interacts only with a small region of the field. Importantly, the vacuum state of the field is not completely uncorrelated. It contains entanglement between different spatial regions. So, when the measurement occurs at point A, it disturbs the local vacuum and extracts some information about the state of the field. This disturbance injects energy into the system, a necessary cost in line with Landauer's principle. Next, the measurement result, a classical piece of information, is transmitted via standard communication channels to a second location, which we can call point B. This step does not involve any quantum entanglement being sent. It is purely classical and bounded by the speed of light. There is no violation of special relativity because no influence travels faster than allowed. Finally, once the measurement result is received at point B, a conditional local operation is performed on the quantum field in that region. The specifics of this operation depend on the earlier measurement result. Because of the pre-existing entanglement between the two regions, this operation causes a rearrangement of the field's state, allowing energy to be extracted locally at point B, despite the fact that nothing has physically traveled from A to B. In effect, energy has been relocated from A to B using a combination of entanglement and information. The injected energy at A, combined with the correlations in the vacuum, makes it possible to extract energy at B, but only after the classical signal is received and the appropriate local operation is executed. One might ask, why go through such an indirect method? Why not simply transmit energy the usual way, through photons, electricity, or heat? The significance of QET is not in its practicality, at least not yet. Rather, it lies in what it reveals about the quantum vacuum. It shows that the vacuum is not just a passive background, but an active medium with extractable energy under the right conditions. It also shows that energy in the quantum regime is not as localized as classical physics assumes. Instead, it can be redistributed using shared entanglement and well-designed operations. Hotta's original formulation of QET was based on spin chains, a model system in condensed matter physics. He showed mathematically that the protocol could be executed using qubits arranged in a one-dimensional array, where measurements and operations affect only neighboring spins. This model provided a clean and rigorous way to explore the basic idea. Later work extended QET to more general quantum fields, including continuous fields like those found in electromagnetism or scalar field theories. In these extensions, QET became even more intriguing. It suggested that even empty space, the vacuum of a field, contains the necessary ingredients for energy extraction, if approached with the right tools. Measurement alters the field, entanglement distributes correlations, classical communication ensures causality, and conditional operations unlock energy at a distance. One of the most fascinating features of QET is that it avoids the transmission of any physical energy carrier. No photons, no particles, no radiation. This distinguishes it from other quantum protocols, such as quantum teleportation of states, where entangled particles are shared beforehand and quantum states are reconstructed elsewhere. In QET, there is no teleportation of quantum states, but rather a redistribution of energy through the manipulation of correlations. This makes QET not only a theoretical curiosity, but a conceptual bridge. It connects quantum information theory, quantum field theory, and thermodynamics in a single framework. It challenges the classical separation between information and energy, and it opens the door to new ways of thinking about the vacuum, not as an inert stage, but as a dynamic participant in physical processes. It is important to emphasize that QET has not yet been demonstrated experimentally in its full form. The concept is still young, and the technical challenges are significant. Creating precise measurements on quantum fields, transmitting classical signals, and executing controlled conditional operations at precise times and locations, all of these require technologies that are still in development. However, Experimental proposals do exist, and simplified versions of the protocol may be testable in the near future, particularly in systems such as ion traps, superconducting qubits, or other engineered quantum platforms. More fundamentally, QET invites us to rethink how energy behaves in the quantum realm. It suggests that energy is not always a thing that moves from one place to another. It can also be something that is revealed or extracted, depending on the structure of correlations and the flow of information. This has implications not only for fundamental physics, but potentially for future technologies. If energy can be extracted from the vacuum using controlled quantum operations, then we may be looking at new forms of energy access or transmission. These possibilities remain speculative for now, but the theoretical groundwork is rigorous and well established. Perhaps most provocatively, QET forces us to ask whether similar processes might occur naturally, not only in the lab, but in the universe itself. If the vacuum is entangled across cosmological distances, could processes like QET play a role in large-scale energy dynamics? Could dark energy, which appears to be uniform and ever-present, be related to some deeper mechanism of energy distribution in the quantum vacuum? These are not questions with easy answers, but they are questions worth exploring. And they begin with a single surprising idea: that energy in the quantum world can be redistributed through entanglement and information without sending anything at all. Having introduced the concept of quantum energy teleportation, we now arrive at the natural and necessary question: how can such a process occur without violating the core principles of physics, especially the two most fundamental constraints in modern science, energy conservation and the speed limit set by special relativity? After all, the idea of transferring energy from one place to another without sending any physical substance through space seems, at first glance, to conflict with everything we know about how the universe works. In classical physics, energy must move through space via a carrier, be it a particle, a wave, or a field excitation. So how can energy appear to be extracted at a distance, guided only by measurements and classical information? To understand how quantum energy teleportation operates within the laws of physics, we must examine the process step by step and, crucially, track how energy flows, where it comes from, and how causality is preserved. The protocol begins with a local measurement at a designated point in a quantum field. Call this point A. The field is initially in its vacuum state, which, as discussed earlier, is not a simple nothing, but a richly entangled configuration filled with zero-point energy. This vacuum contains correlations between different spatial regions, even if they are far apart. The entanglement is not added artificially. It is already there, built into the structure of the vacuum itself. When a measurement is performed at point A, it disturbs the local quantum field. This disturbance requires an input of energy. In quantum field theory, the act of measuring, even passively, necessarily injects energy into the field due to the collapse of the wave function. This is consistent with Landauer's principle, which links the processing of information to thermodynamic costs. The measurement reveals information about the state of the field at A and produces a classical outcome, a number or symbol that records what was found. That classical outcome is then transmitted through ordinary communication channels to a second point, point B, which may be located at a considerable distance. This transmission must obey the limits set by special relativity. It cannot be instantaneous. The information travels no faster than the speed of light. During this interval, nothing happens at point B. There is no energy extraction, no field operation, no measurable effect. Only when the classical information arrives at B can the next step be performed. A local operator, specifically tailored to the measurement result, is applied to the field at point B. This operation is not random. It is conditional on the information received from point A. Because of the pre-existing entanglement between the two regions, the operation at B causes the field configuration there to shift, allowing for the extraction of energy. This energy does not come from the classical signal. Classical information does not carry energy in this context. Rather, the operation unlocks energy already present in the entangled correlations of the vacuum. But it can only succeed if the measurement at A has already occurred, and if the corresponding operation is applied at B. The two steps must be correlated through the shared entanglement and guided by classical information flow. From the standpoint of total energy accounting, everything is balanced. The measurement at A injects energy into the system. The extraction at B withdraws energy, but not more than what was added at A. In fact, the total energy that can be extracted at B is always less than the energy that was injected at A. This ensures that no net energy is created and that energy conservation is strictly preserved. It is helpful to think of the vacuum state not as an absolute zero of energy, but as a reservoir with structure. Measurement disturbs this structure locally, creating a ripple, a disturbance that carries energy and alters correlations. The field remains globally in its vacuum state elsewhere, but the region around A now holds excess energy. When the classical signal is used at B, it acts like a key, allowing the local operator to access the redistributed correlations and release a portion of energy. Because the energy extraction at B cannot occur until the classical information has arrived, causality is preserved. No influence travels faster than light. No signal can be sent from A to B without delay. The entanglement itself is non-local, but it cannot be used to send information on its own. This is a well-known feature of quantum theory. Entanglement enables correlations but not communication. The addition of classical communication ensures that any coordinated action takes place within the bounds of special relativity. Thus, despite appearances, quantum energy teleportation is not a violation of physical law. It is a demonstration of how those laws behave when applied to the quantum vacuum, where information and energy are linked in ways that defy classical expectations. To illustrate this further, consider a useful analogy. Imagine a long, flat landscape covered with a thin, invisible layer of elastic material, something like a trampoline sheet. At any point, you can press down on the sheet, disturbing it locally. That disturbance spreads across the surface, changing the tension everywhere. Now, suppose you know the exact structure of the material, how pressing in one place changes the configuration in another. If someone far away receives a message telling them exactly how you pressed, they could use that knowledge to extract energy by pressing in just the right way at their location. They are not receiving your energy directly, but accessing energy made available through the shared structure of the sheet. Quantum energy teleportation works in a similar way, except the sheet is the quantum vacuum and the tension is encoded in entanglement. The energy does not travel, but the possibility of energy extraction becomes real through shared information. Importantly, this process is not free. The energy extracted at B is always less than the energy injected at A. The protocol does not generate net energy. It redistributes energy in a way that reflects the fundamental symmetries and conservation laws of physics. In practical terms, QET is extremely inefficient under current technological constraints. The measurement must be precise, the communication must be fast, and the field operations must be delicately tuned. Even in idealized models, the energy recovered at B is typically a small fraction of what is input at A. Nevertheless, the importance of QET is conceptual. It demonstrates that energy transfer is not limited to classical pathways. It can occur through informational and quantum correlations, without any direct flow of particles or fields. This represents a new category of physical process, one that belongs neither entirely to thermodynamics nor entirely to quantum mechanics, but to a hybrid regime where both must be considered together. One might wonder if QET could ever be scaled up, if, for example, the vast entanglement of the quantum vacuum across the universe could be used to redistribute energy on cosmic scales. Could nature be using a form of QET already in some hidden process that contributes to the phenomenon we call dark energy? That remains a speculative possibility. But before we can ask that question seriously, we must look at how QET is being tested and how physicists are working to simulate or implement it in real quantum systems. Having established that quantum energy teleportation operates within the boundaries of physical law, the next critical step is to explore whether this elegant theory can be realized in practice. For a concept to transition from abstract mathematics to meaningful science, it must ultimately be testable. Can we design experiments that validate QET? Can energy truly be extracted from a quantum field using measurements and information, not just in equations, but in laboratories? The early formulations of quantum energy teleportation were, by design, theoretical. Masahiro Hotta's original proposal used a simplified system, a spin chain, to show how entanglement and measurement could transfer energy without moving particles. This model was mathematically clear and served to demonstrate the viability of the concept. But spin chains are idealizations, and to move toward real-world verification, the theory needed to evolve into experimental proposals. Over the past decade, physicists have worked to find feasible platforms where the essential ingredients of QET, entanglement, precise local measurements, and controlled operations can be implemented. Several promising systems have emerged as candidates for testing QET in controlled environments. These include trapped ion systems, superconducting qubits, cavity quantum electrodynamics setups, and condensed matter analogues. One of the most compelling areas of exploration has involved solid-state systems, particularly those that can emulate spin chains in laboratory conditions. In 2022, a research team led by Yusa et al. At Tohoku University in Japan published a report describing the implementation of a quantum energy teleportation protocol using a nanowire-based quantum Hall system. While this work did not yet demonstrate full-scale QET as described in field theory, it marked a significant step toward experimental validation of the core principles. The Tohoku experiment used edge channels in a two-dimensional electron gas under a strong magnetic field to mimic one-dimensional quantum systems. These channels allow precise control over the quantum states and offer a highly tunable platform for measurement and manipulation. In this setup, the researchers could perform local operations that interacted with the system's ground state and observe measurable energy responses. Although the full teleportation protocol was not executed, the experiment confirmed the possibility of accessing energy in vacuum-like conditions via local operations, informed by pre-existing quantum correlations. This result reinforced the view that the vacuum, or at least its condensed matter analog, is not an inert backdrop but an active quantum state with extractable energy. It also opened the door to further explorations using engineered quantum materials and nanostructures, where entanglement can be generated and manipulated in highly controlled ways. Elsewhere, teams working with ion traps and superconducting qubits have begun to explore simplified QET-like protocols. These systems are attractive because they allow for near-perfect isolation from environmental noise and precise control over quantum operations. In an ion trap, individual ions can be held in place by electromagnetic fields and their quantum states manipulated with laser pulses. Superconducting qubits, meanwhile, offer fast gate operations and compatibility with scalable quantum circuits. The challenge in these systems is the same: how to faithfully implement the steps of QET, a measurement that perturbs the vacuum or ground state, followed by a classical communication step, and finally a conditional operation that extracts energy at a remote location. Each of these steps involves not just technical difficulty, but conceptual subtlety. The system must remain coherent throughout the protocol. The measurements must be weak enough to preserve correlations, but strong enough to produce useful outcomes. And the operations must be carefully calibrated to match the entangled structure of the system. This balance is delicate, but progress is being made. One particularly interesting approach involves using qubit arrays to simulate quantum fields on discrete lattices. These simulations allow physicists to emulate the dynamics of quantum field theories without needing to build full-scale high-energy experiments. By encoding field variables in qubit states and designing interactions that reproduce field equations, researchers can model vacuum fluctuations, entanglement, and energy extraction in a digital environment. Quantum simulation of field theories is still a young field, but it has already demonstrated impressive results. Several groups have simulated aspects of the Schwinger model, a simplified theory of quantum electrodynamics in one spatial dimension, using digital quantum processors. These simulations provide insights into how particles and fields interact at a fundamental level and could soon be extended to include QET-like protocols. Another area of development is analog simulation, where physical systems are engineered to behave like quantum fields under specific conditions. Optical lattices, created by interfering laser beams to trap cold atoms in periodic potentials, are particularly promising. These systems can mimic scalar fields, spin systems, and other quantum field configurations. Although controlling them precisely remains a challenge, they offer a direct link between theory and laboratory experimentation. As researchers move forward, one of the key goals is to identify observable signatures that confirm QET is occurring. This is non-trivial because the extracted energy is typically very small, often much smaller than thermal noise or background fluctuations. Detecting this energy requires ultra-sensitive measurement tools and careful shielding from environmental disturbances. Nevertheless, the principles of QET are guiding the design of these experiments. Scientists are learning how to calibrate measurements that minimally disturb the vacuum while still yielding usable information. They are developing feedback protocols that condition operations on classical outcomes in real time, and they are analyzing energy balances to confirm that what is extracted at one point corresponds to what was injected elsewhere, all within the limits set by conservation laws. Beyond direct laboratory implementation, physicists are also exploring the implications of QET in more abstract settings, such as holographic duality and quantum gravity models. In some approaches to emergent spacetime, energy teleportation mechanisms could provide insights into how energy is distributed in curved geometries or across horizons. Although these ideas remain theoretical, they reinforce the broader significance of QET, not only as a laboratory protocol but as a conceptual tool for probing the nature of energy, information, and space. Another fascinating line of inquiry concerns the interplay between QET and thermodynamics. Because the energy extracted at the distant point is always less than what was introduced at the measurement point, the process is inherently dissipative. It obeys the second law of thermodynamics and is consistent with entropy increase, yet it achieves something previously thought impossible, a form of energy transfer without physical transport. This invites comparisons with other phenomena such as quantum heat engines, measurement-driven feedback systems, and Maxwell's demon-inspired devices. In all these cases, information plays a central role in extracting useful work from a system. QET represents the most sophisticated version of this idea to date, one that taps into the fundamental structure of the quantum vacuum. Looking ahead, the path to a full demonstration of QET will likely involve continued progress in quantum engineering. As qubit systems grow in scale and fidelity, as simulation platforms become more powerful, and as measurement technologies improve, the conditions required to test QET will come into reach. Whether or not QET ever becomes a practical method of energy transport, its value lies in what it teaches us about the hidden layers of reality. At its core, QET tells us that energy is not merely a local quantity, confined to particles and waves. It is also a relational quantity, shaped by correlations, measurements, and informational flows. That understanding reshapes how we think about empty space, about the boundaries of thermodynamics, and about the fundamental capabilities of quantum systems. And it leads naturally to deeper questions. If QET reveals that vacuum energy can be redistributed through measurement and communication, then what are the broader consequences? Could the vacuum itself, under certain conditions, behave in ways we have not yet imagined, perhaps even contributing to the large-scale dynamics of the universe? As experimental designs begin to probe the feasibility of quantum energy teleportation in real systems, a deeper and more perplexing question emerges, one that reaches beyond technical implementations and into the very foundations of physics. What does it really mean to transfer energy without moving anything? What happens when energy appears at a distant location without any visible intermediary, without any wave or particle making the journey? In the classical view of the universe, energy is intimately tied to motion. If you want to transfer energy from one point to another, you must send something, a mass, a current, a beam of light. Even in electromagnetic theory, where fields can carry energy through empty space, the transfer is mediated by well-defined waves that travel at a finite speed. Energy is conserved, but it is also local. It moves along paths that can be traced, measured, and understood. Quantum energy teleportation, however, invites a different perspective, one in which energy can be relocated, not by physical transmission, but by informational manipulation of an already entangled field. In this picture, energy is not injected into the vacuum at one point and then sent to another through traditional means. Instead, the quantum field is disturbed in one location, classical information about that disturbance is transmitted, and the field is then modified at a second location in such a way that usable energy emerges, all without a direct flow of anything energetic between the 2 points. At first glance, this seems like a contradiction. How can energy show up where nothing traveled? But when viewed through the lens of quantum theory and field dynamics, the process reveals itself as not only consistent, but deeply revealing. It demonstrates that energy is not necessarily a substance that flows like water from place to place. In certain quantum contexts, energy is a potential embedded within correlations, a capacity to do work that depends on the structure of the vacuum and the observer's knowledge of it. One of the key insights here is that quantum fields are not local in the classical sense. The vacuum state, far from being a flat and featureless background, is a global configuration. The entanglement in the vacuum connects regions of space across arbitrary distances. That connection does not transmit signals by itself, but it does mean that operations in one region can have consequences for what is possible in another once classical communication is added. In this way, QET represents a kind of conditional activation of energy extraction. Before the measurement at point A, the quantum field at point B is indistinguishable from any other region of vacuum. After the measurement, and after the classical information is received, the operator at B can perform an action that taps into the previously inaccessible correlations and releases energy. The act is local, but the reason it works is global. This type of process challenges the way we define locality in physics. Traditional locality means that objects are only influenced by their immediate surroundings. But in quantum mechanics, and especially in quantum field theory, locality must be modified to accommodate non-local correlations. These correlations do not allow faster-than-light communication, but they do imply that physical properties in one region depend on conditions elsewhere. In QET, the energy extracted at B is not coming from A in the usual sense. It is coming from the quantum vacuum at B, a vacuum that is not empty but entangled. The process reveals that energy can be contextually released from the vacuum, provided the right conditions are met and the right information is available. In this view, energy becomes something that can be unlocked rather than delivered. This leads to a subtle but profound rethinking of energy itself. In classical mechanics, energy is an observable, a well-defined property of systems that can be calculated and tracked. But in quantum mechanics, observables are tied to the act of measurement. What you measure depends on what you ask and how you ask it. The energy content of a quantum field is not absolute. It depends on the field's configuration, the measurement protocol, and the frame of reference. For example, the Unruh effect, predicted by physicist William Unruh in the 1970s, shows that an observer undergoing constant acceleration through the vacuum will perceive a warm bath of particles, while an inertial observer sees nothing at all. The vacuum is not invariant. It depends on who is looking and how. Similarly, QET implies that the energy accessible in a region of space is not fixed, but contingent. It is shaped by the field's entanglement structure and by the observer's informational access to distant events. Measurement changes the field. Classical information guides operations. And energy, long thought to be a strictly local quantity, turns out to have a non-local dimension. This is not merely a mathematical artifact. It has implications for how we understand space, time, and causality. If energy can be accessed in ways that depend on correlations rather than direct transport, then the structure of space itself must accommodate such processes. It suggests that the geometry of space-time, as described by general relativity, might be emergent from deeper quantum informational principles. Indeed, some theoretical physicists have proposed that space-time itself could be a manifestation of entanglement. In such models, the connectivity of the universe, its geometry, curvature, and even its topology, arises from the pattern of quantum correlations. In this framework, energy teleportation is not an exception to physical law. It is a manifestation of the deeper rules from which those laws emerge. One particularly provocative idea comes from the so-called entanglement wedge reconstruction in the context of the ADAS-CFT correspondence, a holographic duality that connects gravity in a higher dimensional space to quantum field theory on its lower dimensional boundary. In this model, information about the bulk geometry can be encoded in boundary correlations. If spacetime itself is stitched together by entanglement, then processes like QET become natural, even expected. From this vantage point, quantum energy teleportation is not just an exotic protocol, it is a window into the quantum structure of spacetime. It shows that the classical picture, where energy is a substance that moves along trajectories, is only an approximation. The true picture, still emerging from research in quantum gravity and information theory, may be one in which energy, space, and information are all aspects of the same fundamental entity. There are also implications for our understanding of causality. While QET does not allow faster-than-light communication, it demonstrates that causal structure is more subtle than previously believed. The ability to extract energy at one location, conditioned on a distant measurement, reflects a kind of causality that is mediated by correlations rather than signals. This is consistent with quantum theory, but challenges the classical notion that causes must precede effects through direct contact. Perhaps most intriguing is the philosophical shift that QET demands. In traditional physics, energy is a tangible, transportable entity, like a conserved currency. In QET, energy becomes something more contextual, a potential waiting to be unlocked by the right information, in the right place, at the right time. This echoes deeper themes in quantum theory, where properties exist not independently, but relationally. We are left with a remarkable conclusion. Energy need not travel to be transferred. In a quantum universe where entanglement connects distant regions and information shapes what is measurable, energy can be redistributed without motion. This does not break physics, it expands it. And now, having explored the implications of this phenomenon, we are ready to ask the most daring question yet. Could such quantum energy redistribution, subtle, non-local, and built into the vacuum, play a role on cosmological scales? Could it help us explain the greatest mystery in modern cosmology, the accelerating expansion of the universe? If quantum energy can be extracted from a vacuum using entanglement and information, then we must ask a deeper and far more consequential question. Could the universe itself already be entangled across vast distances? If the answer is yes, it could mean that the fabric of spacetime is not only threaded with energy, but also laced with quantum correlations from one region of the cosmos to another. And if those correlations are accessible, then perhaps nature itself is performing operations analogous to quantum energy teleportation on cosmic scales. To explore this idea, we first need to examine the nature of quantum fields, not just in laboratory systems, but in the setting of the universe as a whole. In quantum field theory, the vacuum is not just the lowest energy state, it is also highly entangled. Every region of space shares correlations with its neighbors, and to a degree, with more distant regions as well. These correlations are not visible to the naked eye and cannot be accessed using classical methods, but they are real, measurable, and embedded in the structure of the field itself. In the language of quantum information, we can quantify this entanglement using a concept called entanglement entropy. If you divide a quantum system into two regions, the entanglement entropy measures how much information is shared between them. In most quantum field theories, this entropy scales not with the volume of the region, as one might expect, but with the surface area of the boundary between them. This so-called area law has been verified in many systems and hints at a profound link between quantum correlations and the geometry of space. Now consider that our observable universe spans tens of billions of light years in every direction, and that all regions within it, from clusters of galaxies to the space between atoms, are described by quantum fields. If the vacuum state of these fields is entangled across space, then the universe is not a collection of isolated regions, but a vast and continuous network of quantum connections. One way to probe this question is to look at the early universe. According to the theory of cosmic inflation, the universe underwent a period of rapid expansion just moments after the Big Bang. During this time, quantum fluctuations were stretched to macroscopic scales. These fluctuations seeded the large-scale structure we observe today, the distribution of galaxies, clusters, and voids. But those same fluctuations also carried quantum correlations. Inflation did not destroy entanglement, it amplified it. Regions that were once causally connected were pulled apart faster than light could travel between them, yet the correlations embedded in the quantum fields were preserved. In this view, parts of the sky that are now separated by billions of light-years may still share entangled origins. This idea is not merely poetic, it has been explored in serious cosmological models. In the 2010s, physicist Seth Lloyd and collaborators proposed that the universe could be treated as a quantum computation, a kind of giant quantum circuit that evolved from a highly entangled initial state. In such models, spacetime itself emerges from the pattern of entanglement. That is, geometry is not fundamental, it is a product of correlations. Other researchers have taken this idea further. The ADS-CFT correspondence, developed in the late 1990s by Juan Maldacena, showed that a theory of gravity in a higher dimensional space, anti-de Sitter space, could be mathematically equivalent to a quantum field theory on its lower dimensional boundary. This holographic duality suggested that gravitational dynamics, including black hole physics, could be described purely in terms of quantum entanglement. Inspired by this, physicists like Mark van Ramsdonk proposed that the very connectivity of spacetime, the reason regions of space are linked into a continuous fabric, might arise from quantum entanglement. Without entanglement, the theory suggests, space itself would fall apart into disconnected pieces. This is a radical view, but one supported by increasingly sophisticated theoretical work. If these models are correct, if spacetime and geometry are emergent from quantum information, then it follows that entanglement is not an occasional or exotic feature of the universe. It is its foundation. Every region of space may be connected to every other, not by direct contact, but by shared correlations. In that case, the precondition for quantum energy teleportation, namely entanglement between distant points, is already present on a cosmic scale. This would have enormous implications for how we think about vacuum energy and dark energy. If entanglement stretches across cosmological distances, and if local operations informed by measurement can extract energy from the vacuum, then the possibility arises that nature itself may engage in processes analogous to QET, not deliberately, of course. There is no cosmic operator performing measurements and sending messages, but as part of the physical dynamics of the universe, information and entanglement may play roles in the redistribution of energy. Could this help explain the observed acceleration of the universe's expansion? That question remains speculative. But what is no longer speculative is the recognition that entanglement is a widespread, robust, and persistent feature of quantum fields, even in curved space-time. One of the key pieces of evidence supporting this view comes from black hole thermodynamics. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes have entropy proportional to the area of their event horizon. This was a strange result. Entropy, which measures disorder or information content, should scale with volume, not area. But in black holes, it seemed to be an exception. Later work showed that this area scaling of entropy was not limited to black holes. In many quantum field theories, the entanglement entropy between a region and its surroundings also scales with the area of the boundary. This connection suggested that the entropy of black holes, and possibly of spacetime itself, is actually entanglement entropy. In other words, the information about what lies inside a region of space may be encoded on its surface, and the structure of spacetime within may be determined by quantum correlations across that surface. This is the principle behind holographic theories of gravity, theories in which the physics of a volume is fully encoded in lower dimensional data. If this is true for black holes, it may also be true for the universe as a whole. The cosmos could be a vast holographic system in which distant regions are correlated not by chance, but by design, a design written into the quantum fabric from the beginning of time. This brings us back to quantum energy teleportation. In lab systems, QET relies on entanglement that is created intentionally. Two particles, or two regions of a field, are entangled through interaction. But in the universe, that entanglement may already be there. Inflation, vacuum fluctuations, and the quantum origins of spacetime may have built an entangled structure from the outset. If so, then the conditions for QET are not rare, they are universal. The remaining ingredient, classical communication, would not be present in the same way as in lab-based protocols. There is no central observer sending messages between galaxies. But if local field dynamics are capable of exploiting correlations embedded in the vacuum, then something akin to QET may occur as part of the universe's natural evolution. Perhaps the vacuum energy we observe today, the energy driving cosmic acceleration, is not a fixed quantity, but an emergent one, shaped by the entanglement of the fields that define space itself. These ideas remain on the frontier of physics. They are not yet confirmed by experiment, nor are they part of the standard cosmological model. But they are consistent with what we know about quantum fields, inflation, and the role of entanglement in shaping the observable universe. They offer a new framework, one in which energy, space, and information are woven together into a single tapestry. Now that we've examined the possibility that quantum entanglement exists across the entire universe, the next question becomes inescapable. Could quantum energy teleportation, or a process fundamentally like it, be linked to the value of the cosmological constant? In other words, might the subtle, distributed rearrangement of vacuum energy through quantum correlations provide not only a theoretical curiosity, but a physical mechanism behind the mysterious force driving the universe's accelerated expansion? To investigate this, we must return to the cosmological constant itself, the lambda term introduced by Albert Einstein to allow for a static universe, later discarded and then resurrected when observations revealed that cosmic expansion is not only continuing but accelerating. Lambda, in the modern understanding, is equivalent to a vacuum energy density, an energy embedded in space itself, exerting a repulsive gravitational effect. The cosmological constant problem, as previously discussed, arises because quantum field theory predicts that the vacuum energy should be staggeringly large, many orders of magnitude greater than what is observed. The small but non-zero value we do measure suggests that something must either cancel out the enormous vacuum contributions or regulate them in a way we do not yet understand. It is here that quantum energy teleportation might offer a fresh perspective. Traditionally, physicists have treated vacuum energy as a static quantity, a kind of background field that fills space uniformly. But what if the vacuum is not simply filled with energy, but continuously reshaping it? What if energy is being redistributed through entanglement and local field interactions in a way that leads to a net effect resembling a small, persistent cosmological constant? This would imply that what we observe as dark energy, the source of cosmic acceleration, is not a uniform pressure from an immutable vacuum, but the statistical residue of a deeper, dynamical process. That process, in turn, could resemble QET on a vast scale. To see how this might work, recall that in quantum energy teleportation, energy is not transmitted from point A to point B through physical carriers. Instead, it is extracted at B after a measurement at A, conditional on shared entanglement and classical information. The field itself is modified locally, and energy is redistributed rather than transported. In a cosmological context, there is no external agent performing measurements and sending messages. But if quantum fields are inherently entangled, and if they evolve in ways that mimic the local measurement and conditional operation steps of QET, even in a statistical or emergent sense, then the vacuum might naturally support a process of continual micro-level energy rearrangement. Over large scales, this could average out to the effect we interpret as a small positive vacuum energy. This approach does not require the fine-tuning of parameters or the introduction of exotic new particles. It builds directly on known principles, the entanglement of quantum fields, the ability of local operations to extract or inject energy, and the fundamental role of measurement-like interactions in modifying field configurations. Moreover, this perspective could help explain one of the most puzzling aspects of the cosmological constant, its timing. Observational data suggests that dark energy only began to dominate the dynamics of the universe relatively recently, long after the formation of galaxies and large-scale structures. In earlier epochs, matter and radiation were the dominant components. Why then is the vacuum energy becoming relevant now? If the cosmological constant is not fixed, but instead emerges from dynamical quantum processes, its influence could vary over time. Perhaps entanglement patterns in the vacuum change as the universe expands, subtly shifting the balance of extractable and injected energy. the statistical structure of the vacuum could evolve, leading to a delayed onset of the repulsive force we now attribute to dark energy. This time-dependent behavior would be difficult to reconcile with a truly constant lambda, but it fits naturally with a model in which the vacuum energy we observe is not a fundamental parameter but an emergent phenomenon, the result of countless tiny exchanges, adjustments, and correlations happening beneath the level of classical observation. Masahiro Hotta, the originator of QET, has speculated in this direction. In some of his theoretical work, he has explored whether quantum energy teleportation can be generalized beyond lab-based protocols and applied to curved spacetime. If so, then QET-like processes could become part of the universe's natural energy landscape, subtly influencing the evolution of spacetime itself. This would make lambda not a fundamental constant in the usual sense, but a kind of emergent average, a macroscopic expression of microscopic processes that redistribute energy without violating causality or conservation. In this framework, the vacuum energy is not a problem to be cancelled or tuned, but a phenomenon to be understood as arising from the quantum structure of spacetime. There are potential parallels here with ideas from quantum thermodynamics. In that field, systems can maintain steady-state behaviors, including persistent energy flows, without external driving forces, as long as certain statistical conditions are met. These non-equilibrium steady states are not fine-tuned. They emerge naturally from the underlying interactions and constraints. Could the cosmological constant be such a steady state? A long-term average resulting from subtle energy redistribution driven by the entanglement structure of the vacuum. This idea is not yet fully developed, but it offers a compelling direction for further research. It also aligns with growing interest in the role of quantum information in gravity and cosmology. From the Bekenstein-Hawking entropy formula to holographic dualities to recent work on the quantum nature of spacetime geometry, physicists are increasingly recognizing that information is not just an abstract concept, it is a physical resource on par with energy and momentum. If spacetime is emergent from entanglement, and if vacuum energy is shaped by informational flows, then the cosmological constant becomes part of a broader story, one that unifies quantum theory, thermodynamics, and geometry in a single framework. There are, of course, many challenges ahead. Testing this hypothesis will not be easy. The effects of quantum energy teleportation are small and subtle, even in controlled laboratory conditions. Extending those ideas to cosmology involves extrapolations that are not yet fully justified by data. Still, the logic is internally consistent, and it builds on well-established physics rather than speculative extensions. Perhaps future observations of the cosmic microwave background, of gravitational waves, or of the fine structure of cosmic expansion will reveal patterns that hint at dynamical vacuum processes. Or perhaps simulations of quantum fields in curved spacetime will uncover signatures of emergent energy flow. Whatever the path, the pursuit is worth the effort. Reframing the cosmological constant as a product of quantum information dynamics not only gives us a new tool to approach dark energy, it also reframes what it means to talk about nothing. The vacuum, long thought to be inert, becomes a dynamic participant in the story of the universe, and energy, long thought to be a purely local mechanical quantity, becomes a relational and emergent property of quantum correlations. If the cosmological constant can be interpreted as a product of vacuum entanglement and the subtle redistribution of energy, then we are drawn to an even more profound possibility that dark energy itself may not be a thing at all. It may not be a fundamental field, nor a substance filling space, nor even a constant in the traditional sense. Instead, it may be an emergent phenomenon, something that arises not from the input of external energy, but from the collective behavior of spacetime and quantum information. This shift in perspective invites us to look at the deep structure of physical law from a new angle. In physics, emergence refers to the appearance of patterns, behaviors, or properties that are not obvious from the fundamental laws governing the smallest parts of a system. Emergence is how temperature arises from the motion of individual particles. It is how a ripple on a pond arises from the collective motion of countless water molecules. And increasingly, many physicists are exploring the idea that gravity itself, and by extension, the expansion of the universe, could be emergent. One of the most influential voices in this area is Dutch theoretical physicist Erik Verlinde. In the early 2010s, Verlinde proposed that gravity might not be a fundamental force, but rather an emergent entropic force, one that arises from the statistical behavior of microscopic degrees of freedom. His model was inspired by ideas from thermodynamics, black hole entropy, and the holographic principle, and it built upon earlier insights from Jacob Bekenstein, Stephen Hawking, and Ted Jacobson. Verlinde's approach begins with a simple question: what if spacetime itself is not fundamental, but instead emerges from information? In this view, the geometry of the universe is not a backdrop, but a product, a large-scale consequence of quantum correlations and statistical mechanics. Gravity, then, is not a force that acts across space, but a tendency for systems to maximize entropy, driven by underlying informational structures. Ted Jacobson's work from the mid-1990s offered a particularly elegant demonstration of this principle. He showed that Einstein's field equations, the very foundation of general relativity, could be derived from thermodynamic principles, specifically the Clausius relation, which relates heat, temperature, and entropy. In Jacobson's model, if one assumes that the area of a local causal horizon corresponds to entropy and that energy flow across that horizon produces entropy change, then the equations of general relativity follow naturally. This result hinted strongly that gravity might be a kind of statistical phenomenon, not imposed from above, but arising from below. These ideas were further developed by other theorists who connected the dots between entanglement entropy, space-time geometry, and the dynamics of the vacuum. If space and time emerge from quantum entanglement, and if the geometry of space-time is shaped by the distribution of that entanglement, then perhaps dark energy, the phenomenon we observe as cosmic acceleration, is also a byproduct of this structure. In this emergent picture, what we call dark energy is not sourced by a new particle or a mysterious fluid. Instead, it may reflect the collective behavior of quantum correlations spread across the universe. Just as temperature arises from countless random motions, the cosmological constant may arise from the statistical behavior of entangled quantum fields. This idea is supported by insights from the holographic principle, which suggests that all the information contained in a volume of space can be encoded on its boundary. Originally proposed by Gerard 't Hooft and refined by Leonard Susskind, the holographic principle finds its most precise formulation in the ADS-CFT correspondence, a duality that equates a gravitational theory in a higher dimensional space with a quantum field theory on its lower dimensional boundary. In this context, space-time geometry and all the forces and fields within it can be understood as emergent from the dynamics of the boundary theory. Gravity, vacuum energy, and even expansion can be seen as coarse-grained phenomena, much like thermodynamic pressure or heat. When this principle is applied to cosmology, it suggests that the universe's expansion might be the result of entanglement patterns across its causal horizon. In other words, the large-scale structure and dynamics of the cosmos, including dark energy, might be governed not by local fields, but by the information encoded at the universe's boundary. One of the appealing features of this idea is that it helps address the problem of fine-tuning. Traditional models struggle to explain why the cosmological constant is small but non-zero. Emergent models, by contrast, suggest that the value of lambda may be a kind of thermodynamic equilibrium, the natural consequence of how space, time, and information arrange themselves. Just as the pressure of a gas is not fine-tuned but follows from the system's state variables, so too might dark energy reflect an equilibrium of the quantum vacuum. This would mean that dark energy is not a separate entity, not an external driver of acceleration, but a reflection of the universe's informational state. Its value might be determined not by particle physics, but by the global entanglement structure of spacetime. This perspective offers a unifying framework in which gravity, expansion, and vacuum energy all emerge from the same foundational ingredients. Of course, this is still a developing area of research. The mathematics of emergent gravity is complex, and the experimental evidence remains circumstantial. While models such as Verlinde's reproduce certain cosmological observations, they must still be tested against precision data from cosmic microwave background measurements, galaxy surveys, and gravitational wave observations. Nevertheless, the conceptual shift is significant. It encourages us to stop looking for dark energy as a missing piece and start asking whether the entire puzzle might be a projection, a large-scale manifestation of quantum information processes happening beneath the surface. Quantum energy teleportation fits naturally into this emergent framework. It shows that energy can be manipulated through informational means without direct transmission. It demonstrates that the vacuum is not static but responsive to measurement and structure, and it provides a mechanism by which energy can be accessed, relocated, or reinterpreted based on correlations rather than carriers. In the emergent view of spacetime, processes like QET may be more than laboratory curiosities. They may be miniature reflections of how the cosmos operates at scale. Entanglement, measurement, information flow. These are not fringe phenomena. They may be the very code from which reality is written. If that is the case, then our understanding of dark energy must change accordingly. Rather than treating it as a mystery to be resolved through particle physics, we might begin to see it as a clue, a signature of the deeper quantum structure of the universe, an effect that points not to new matter, but to new relationships among the old. And so, as we trace this path from quantum fields to cosmic geometry, from information theory to dark energy, we find ourselves on the edge of a larger synthesis, one where physics is no longer divided into domains, but unified by principles that apply from the smallest scales to the largest. If dark energy, the cosmological constant, and even space-time itself might be emergent from quantum information, then it becomes natural to turn our attention to black holes, the most extreme arenas in the universe where gravity, quantum mechanics, and information all collide. These cosmic objects, formed from the collapse of massive stars or the coalescence of matter in the early universe, have long served as natural laboratories for testing the boundaries of physics. But more than that, black holes have fundamentally reshaped our understanding of energy, entropy, and the fate of information. The classical description of a black hole is deceptively simple: a region of space-time from which nothing, not even light, can escape. Defined by an event horizon, the invisible boundary beyond which escape is impossible, a black hole in general relativity can be fully described by just three quantities: its mass, its electric charge, and its angular momentum. This is known as the no-hair theorem. In this view, black holes are featureless, swallowing everything they absorb and revealing nothing about what went in. But the quantum perspective began to challenge this picture in the latter half of the 20th century. In the early 1970s, physicist Jacob Bekenstein proposed that black holes should have entropy, a measure of the number of microscopic configurations consistent with their macroscopic appearance. He noticed that a black hole's entropy seemed to scale with the area of its event horizon, not its volume. This was a radical idea, suggesting that the information content of a black hole was proportional to its surface, not its interior. Bekenstein's proposal gained greater significance when Stephen Hawking, a few years later, showed that black holes are not entirely black. By applying quantum field theory to curved spacetime, Hawking discovered that black holes emit radiation, now called Hawking radiation. This radiation arises from quantum fluctuations near the event horizon. Pairs of virtual particles spontaneously form. One falls into the black hole, while the other escapes, becoming real and observable. Over vast timescales, this process allows the black hole to lose mass and eventually evaporate completely. Hawking's result was monumental. It combined gravity, quantum mechanics, and thermodynamics in a single framework, and suggested that black holes have a temperature, emit thermal radiation, and possess entropy. The Bekenstein-Hawking entropy formula, 1/4 of the event horizon area, measured in Planck units, became a cornerstone of quantum gravity research. But this insight also gave rise to a paradox, one that has haunted theoretical physics ever since. If black holes evaporate, and if the radiation they emit is purely thermal, carrying no information, then what happens to the information that fell into the black hole? Is it lost forever? This is known as the black hole information paradox. According to quantum mechanics, information must be preserved. The evolution of a closed system should be unitary, meaning that the initial state can always be reconstructed from the final state. But Hawking's calculations seem to imply otherwise. Once a black hole completely evaporates, all the information it swallowed would be gone, violating a core principle of quantum theory. Many possible resolutions have been proposed over the years. Some suggest that the information is somehow encoded in the Hawking radiation itself, though in a highly scrambled form. Others propose that it is preserved in a remnant, a tiny leftover of the black hole that stores the data. More speculative ideas involve wormholes or modifications to the structure of spacetime at the Planck scale. One of the most intriguing proposals comes from the field of holography. Building on the idea that the entropy of a black hole scales with area, physicists like Gerard 't Hooft and Leonard Susskind developed the holographic principle. This principle posits that the description of a volume of space can be encoded on its boundary, much like a hologram encodes three-dimensional information on a two-dimensional surface. In this framework, black holes, and potentially the entire universe, can be described in terms of boundary data. The ADS-CFT correspondence, formulated by Juan Maldacena in the late 1990s, made this idea concrete. It showed that a gravitational theory in anti-de Sitter space is equivalent to a quantum field theory without gravity on the boundary of that space. In other words, space-time, gravity, and all their dynamics emerge from a lower dimensional quantum system. This holographic viewpoint offers a resolution to the information paradox. If the boundary theory is unitary, then so must be the bulk theory. Information is not lost, it is encoded in the correlations among the Hawking radiation particles, albeit in an extremely subtle and complex way. What does this have to do with energy teleportation or dark energy? The connection lies in the recognition that information flow, energy flow, and space-time dynamics are not independent. They are deeply interwoven. In the process of black hole evaporation, energy is released as radiation, but that energy carries with it an imprint of the black hole's internal correlations. If that information can be reconstructed, as recent work with so-called quantum extremal surfaces and the island rule suggests, then energy and information are indeed coupled even in the most extreme environments. More than that, the entire structure of the black hole, including its event horizon, thermodynamic properties, and radiation, can be understood as arising from entanglement. Just as quantum energy teleportation redistributes energy through measurement and shared correlations, the Hawking process shows how energy can be radiated by leveraging the entangled structure of the vacuum. This brings us to a broader principle. Energy is not merely transferred through particles or waves. It can emerge from the reorganization of quantum correlations, especially near boundaries and horizons. The event horizon of a black hole is a kind of natural interface, a surface across which quantum field configurations are tightly constrained. It functions not unlike the boundary between two subsystems in QET. When viewed this way, the black hole becomes a cosmic analog of the QET process. Inside the horizon, information is inaccessible. Outside, it becomes gradually available through radiation. The field is altered not by physical transport, but by the shifting structure of entanglement and vacuum fluctuations. The process is local and causal, yet globally it results in a redistribution of energy and entropy. This insight supports the idea that energy, in the quantum world, is inherently linked to information flow. Measurement, entanglement, and field structure define what energy is accessible, where, and how. If this principle holds true at the event horizon of a black hole, the most extreme known boundary in nature, then it may also hold true in the more subtle, diffuse vacuum of cosmological space. From this viewpoint, black holes are not just puzzles to be solved, they are models, perhaps the clearest examples we have, of how energy, space, and information interact at the quantum level. And if dark energy is indeed a large-scale manifestation of quantum vacuum structure, then studying black holes may reveal more than just their secrets. It may reveal our own universe's inner workings. As we consider this possibility, a new question arises. If black holes show us how energy and information flow at the edge of physics, could similar principles operate across the entire cosmos? Could quantum energy teleportation, entanglement, and emergent gravity combine to shape not just local processes, but the universe's global expansion? Having seen how quantum information flow manifests in the extreme environments around black holes, and how energy can emerge from entanglement and boundary interactions, we are now prepared to explore a bolder possibility. Could processes like quantum energy teleportation, or something closely related to it, be operating on the grandest scale of all, shaping the dynamics of the entire universe? Could the accelerating expansion of space be powered not by a hidden substance or field, but by the collective behavior of entangled quantum fields spread across the cosmos? To consider this seriously, we must reflect on the nature of cosmic acceleration. Observations over the last few decades, from supernova surveys, galaxy clustering, and measurements of the cosmic microwave background, have all pointed to one unsettling conclusion. The universe is not merely expanding, the rate of expansion is increasing. Whatever force is driving this acceleration must be repulsive on cosmological scales, uniform across space, and persistent over time. The standard model of cosmology accounts for this with a cosmological constant, a fixed, non-zero vacuum energy density that exerts negative pressure. But as we have explored, this explanation creates a profound theoretical tension. The predicted vacuum energy from quantum field theory is vastly too large, and the observed value appears unreasonably fine-tuned. Moreover, the timing is peculiar. Dark energy only began to dominate the universe's expansion relatively recently on cosmic timescales. Quantum energy teleportation may offer a conceptual way forward, not necessarily as the exact mechanism of cosmic acceleration, but as a model that captures the kind of energy behavior the universe might be exhibiting. At its core, QET shows that energy can be extracted from the vacuum, not by injecting power or particles, but by accessing and manipulating pre-existing entanglement. If such processes are possible in principle, and potentially even occurring naturally, then perhaps the energy that appears to be pushing the universe apart is in fact being continuously restructured at the quantum level. Imagine the quantum vacuum as a vast, entangled substrate, spanning the observable universe and beyond. This vacuum is not empty, it seethes with fluctuations and correlations, even across regions that appear causally disconnected. If these correlations can be accessed, not by intelligent agents, but by the universe's own internal dynamics, then energy may be redistributed across space continuously and subtly. In this view, what appears as a uniform vacuum energy might actually be an emergent property of countless microscopic redistributions of energy occurring throughout the cosmos. These redistributions would not violate any conservation law. They would involve no superluminal signaling, no particles traveling faster than light. Rather, they would reflect a natural flow of energy governed by entanglement structure and field interactions, just as QET operates in laboratory models. This leads to an important distinction. Perhaps the cosmological constant is not a constant in the strictest sense. It may be a statistical average, a large-scale residue of quantum field activity that, when viewed across billions of light-years, appears uniform. Locally, the vacuum might be fluctuating and interacting with matter and radiation in complex ways, but when we observe it from a cosmological perspective, the result is smooth and steady expansion. In such a framework, the energy driving cosmic acceleration is not coming from an external source, it is being tapped from within, from the structure of the vacuum itself, and the mechanism for that tapping might resemble quantum energy teleportation, local operations extracting or releasing energy based on distant correlations. Of course, QET as a protocol involves explicit measurement and conditional operations. In the universe, there are no observers taking measurements in the traditional sense, but quantum field interactions themselves may serve a similar role. Fields interacting through nonlinear dynamics may perform effective measurements on each other. Decoherence, the process by which quantum systems lose coherence due to environmental interaction, can spread correlations through space, effectively redistributing energy. If such processes are ubiquitous, then the entire cosmos may be engaged in a quiet, ongoing restructuring of its own vacuum. This would also help explain why dark energy became dominant only after the universe had expanded sufficiently. In the early universe, when matter and radiation were dense and highly energetic, their influence on vacuum structure may have suppressed long-range entanglement patterns. As the universe expanded and cooled, these correlations could become more accessible, allowing vacuum energy to express itself more fully. The transition from matter-dominated to dark energy-dominated expansion may therefore mark a shift in how the vacuum interacts with the rest of the universe. Once the density of conventional matter dropped below a certain threshold, the vacuum's quantum correlations could begin driving expansion more directly. If this is the case, then dark energy is not a fixed background field, but a dynamic participant in cosmic evolution. It does not act alone, but as part of an emergent system, one shaped by the entanglement and interaction of quantum fields on all scales. From this perspective, the expansion of the universe is not a passive response to a cosmological constant. It is an active process, continuously sustained by the internal structure of spacetime itself. There are important implications to consider. First, if QET-like processes help shape the vacuum's energy distribution, then the cosmological constant could evolve slowly over time. This is distinct from models like quintessence, which posit a rolling scalar field. Instead, the vacuum energy would remain approximately constant on large scales, but subject to slow variation due to shifting entanglement dynamics. Second, such a model could help resolve the coincidence problem, the question of why the vacuum energy density is of the same order of magnitude as the current matter density. In a QET-informed view, vacuum energy emerges in relation to matter, not in isolation from it. The dynamics of the quantum vacuum may respond to the presence and distribution of matter, allowing dark energy to become significant only when the matter density falls below a certain level. Third, this framework could unify ideas from quantum gravity, holography, and thermodynamics. If energy is not a standalone substance, but a manifestation of quantum information flow, then the same principles that govern QET in laboratory systems might apply to cosmology. The structure of spacetime, the flow of time, and the acceleration of expansion may all be facets of a deeper informational substrate. While these ideas remain speculative, they point to a compelling direction for theoretical and observational research. Advanced cosmological simulations may be able to test whether subtle variations in vacuum energy can arise from quantum field dynamics. Precision measurements of dark energy's equation of state may reveal time dependence or spatial anisotropies. And quantum technologies may soon allow for experimental analogues of QET in highly controlled settings, providing insights into how such processes could operate on larger scales. In the end, the central idea remains remarkably simple, even elegant. Perhaps the universe powers itself. Perhaps energy is not injected from beyond, but unlocked from within, by the very structure of quantum spacetime. And if that is true, then the mystery of dark energy becomes not a search for a new force, but a recognition of a hidden order, an order that links energy, information, and geometry in a continuous and self-sustaining dance. Although the idea that quantum energy teleportation could help explain dark energy is both elegant and conceptually appealing, it remains highly speculative. Any theory that seeks to revise or extend our understanding of the vacuum, spacetime, or the accelerating expansion of the universe must meet a very high standard of scientific scrutiny. This means addressing not only the technical and theoretical challenges, but also the critical perspectives of physicists who demand clear testability, internal consistency, and alignment with existing data. To begin with, it is important to acknowledge that quantum energy teleportation, as originally formulated by Masahiro Hotta and other researchers, was designed as a theoretical protocol, not as a model of cosmological dynamics. It was constructed within well-defined systems, such as spin chains or idealized quantum fields, and its goal was to demonstrate the possibility of redistributing energy through local operations conditioned on entanglement and classical communication. This is quite different from proposing that a similar process operates naturally, spontaneously, or continuously across cosmic distances. Making that leap requires a series of theoretical assumptions and extrapolations, many of which have yet to be fully justified. One major criticism centers around the scalability of QET. The energy transferred in most QET protocols is extraordinarily small, often many orders of magnitude below thermal noise in any real system. In a cosmological setting, the question becomes, can a process that is so subtle and resource-intensive in the lab really be generalized to account for a phenomenon as large as cosmic acceleration? Supporters might argue that even small processes, if they occur throughout the entire vacuum and over vast periods of time, could have cumulative effects. But critics respond that such reasoning must be made precise. How does one quantify the collective influence of QET-like energy redistribution across an entire universe? What equations govern this redistribution? How are the correlations structured, and how do they evolve? Another issue involves the role of measurement and communication. In traditional QET, a measurement must be made at one location, and the result must be transmitted classically to another location where the energy is then extracted. This is a carefully orchestrated sequence. In the universe at large, there are no external agents performing measurements or sending messages. So if QET-like behavior is to occur naturally, what counts as a measurement? What serves the role of the classical communication channel? Some theorists have proposed that interactions between quantum fields themselves, especially those involving decoherence, scattering, or entanglement with local matter, might serve as effective measurements. Still, the details of how this would work remain underdeveloped. No comprehensive model currently describes spontaneous QET in a cosmological vacuum in a way that can be rigorously tested. Skeptics also point out that quantum field theory, while extremely successful in particle physics, has not yet been fully unified with general relativity. This means that any claims about how vacuum energy behaves in curved spacetime must be treated with caution. The true nature of quantum gravity is still unknown, and it is possible that a more complete theory could reveal mechanisms that either support or contradict the QET framework. Another open question concerns energy conservation in curved spacetime. In general relativity, global energy conservation is more subtle than in flat spacetime. Energy cannot always be defined as a single conserved quantity across all of spacetime, especially in an expanding universe. This complicates efforts to model QET-like processes on cosmological scales. If energy is locally conserved but not globally well defined, what exactly is being teleported? Furthermore, while entanglement entropy and the holographic principle offer tantalizing hints about the relationship between information and geometry, these insights are not yet part of a complete theory of emergent spacetime. Much of the current work is highly mathematical, relying on models that may not apply directly to our universe, such as those using anti-de Sitter space rather than the de Sitter geometry associated with cosmic acceleration. From a practical standpoint, experimental verification of QET remains a major hurdle. While some progress has been made in simulating aspects of the protocol in condensed matter systems and trapped ions, no experiment has yet demonstrated energy teleportation over macroscopic distances in a quantum field. The technical challenges are immense, isolating quantum systems from environmental noise, performing weak measurements, and executing conditional operations with extreme precision. Even if these challenges are overcome, scaling the results up to draw conclusions about cosmology will not be straightforward. What holds in a one-dimensional spin chain or a tabletop quantum device does not automatically apply to the full complexity of the quantum vacuum in four-dimensional spacetime. Finally, there is a philosophical concern. The idea that energy can be extracted based on pre-existing correlations without anything traveling through space challenges our classical intuition. Although QET does not violate causality or conservation laws, it still feels, to some, like a kind of cheating, an overly clever trick that may obscure more than it reveals. Physicists are right to demand that new theories not only solve problems, but also deepen our understanding in a transparent and testable way. Despite these criticisms, it is important to recognize what QET and related ideas have already contributed. They have highlighted the fact that the vacuum is not empty, but structured. They have reinforced the idea that energy and information are linked in ways far more profound than classical physics allows. They have offered models, even if incomplete, for how non-local correlations might influence local dynamics, and they have provided fresh conceptual tools for thinking about dark energy and the nature of spacetime itself. The value of a theory is not always in its immediate predictive success, but in its capacity to reframe the questions we ask. Quantum energy teleportation, whether or not it turns out to play a role in cosmology, has already done this. It has forced physicists to reconsider what it means for energy to move, what it means for space to expand, and what it means for the vacuum to act. As research continues, there will likely be refinements, alternatives, and perhaps even radical departures from the current QET model. But the broader shift toward viewing energy as informational, space-time as emergent, and the vacuum as active will endure. Despite the unresolved questions and valid criticisms surrounding quantum energy teleportation and its speculative connection to dark energy, the horizon of scientific inquiry remains wide open. Rather than undermining the value of these ideas, the current limitations serve to clarify the direction of future research. If we hope to understand whether QET-like processes play a role in cosmic acceleration, or even if they simply teach us something new about the quantum vacuum, we will need a concerted effort spanning theory, experimentation, and observation. The first avenue for progress lies in the continued development of quantum information theory as it applies to spacetime and energy. Theoretical physicists are already working to better understand how entanglement, measurement, and energy redistribution relate to one another in quantum field theory. Much of this work is still framed in simplified or idealized systems, but the tools are improving rapidly. Quantum simulation is emerging as a particularly powerful tool in this regard. By constructing quantum systems that mimic the behavior of complex fields, researchers can test how entanglement affects local energy distributions and whether QET-like protocols can be extended beyond idealized spin chains. Quantum simulators built from superconducting qubits, trapped ions, or ultra-cold atoms in optical lattices now allow physicists to explore dynamics that were previously accessible only in abstract mathematics. These simulators are already being used to model small-scale versions of black hole evaporation, quantum phase transitions, and even holographic dualities. It is not difficult to imagine future experiments in which quantum energy teleportation is demonstrated with increasingly sophisticated setups, perhaps even in 2- or 3-dimensional fields that more closely resemble the fabric of space-time. But simulation alone is not enough. Ultimately, to bridge theory with the cosmos, experimentalists will need to explore physical systems where vacuum energy, entanglement, and information flow can be tested with high precision. This may require new generations of ultra-sensitive instruments designed to measure small energy shifts in near-vacuum conditions or to detect correlations between spatially separated regions of a quantum field. One promising direction is the refinement of Casimir force measurements, experiments that detect the tiny attractive or repulsive forces between metal plates in a vacuum caused by quantum fluctuations. These experiments have already confirmed that the vacuum is not truly empty. With further sensitivity, it may become possible to probe whether that vacuum energy can be influenced or modulated in ways that mirror QET predictions. Another possibility lies in gravitational wave astronomy. As instruments like LIGO, Virgo, and CAGRA become more sensitive, and as the next generation of detectors, such as the Laser Interferometer Space Antenna, LISA, is deployed, physicists will gain access to the fine structure of space-time at an unprecedented level. While these detectors are not designed to measure vacuum energy directly, they may reveal subtle features of gravitational dynamics that can be compared with emergent space-time models. On the cosmological front, efforts to characterize dark energy more precisely continue with missions like the European Space Agency's Euclid Telescope and NASA's upcoming Nancy Grace Roman Space Telescope. These observatories aim to map the distribution of galaxies and cosmic structures over time, shedding light on how the universe's expansion rate has evolved. If the effects of dark energy deviate even slightly from the predictions of a pure cosmological constant, it may point toward a dynamic vacuum, perhaps one shaped by informational processes like those described in QET. At the same time, theoretical research in quantum gravity continues to explore deeper frameworks in which QET-like behavior could naturally arise. In particular, developments in the holographic principle, entanglement wedge reconstruction, and tensor network models of spacetime suggest that the geometry of the universe may indeed be woven from quantum information. If these models can be made predictive, connecting entanglement structure with measurable quantities like curvature or vacuum energy, they could offer indirect ways of testing the emergent spacetime hypothesis. Educational and institutional collaboration will also be essential. The intersection of quantum information science, cosmology, and fundamental physics requires cross-disciplinary fluency. It demands researchers who can think both like a field theorist and like a quantum engineer. Fortunately, many institutions are beginning to support this kind of integrated work. Graduate programs now include tracks in quantum computing with relevance to high-energy physics, and research centers focused on quantum foundations are increasingly engaging with gravitational physics. Moreover, new technological infrastructure is making it easier to share code, simulations, and datasets across borders. As quantum computing platforms become available to researchers through cloud services, and as cosmological surveys generate petabytes of data, the opportunity for collaborative discovery grows. Philosophically, this line of research invites us to rethink not only the nature of energy and space, but the relationship between knowledge and reality. Quantum energy teleportation hinges on the idea that what we know, or can know, about a system affects how we can interact with it energetically. If this principle extends beyond the lab, then the universe itself might be understood as a system that encodes and manipulates information on every scale. In that sense, the study of dark energy through the lens of QET becomes not just a search for an explanation of cosmic acceleration, but a deeper investigation into what it means to exist in a quantum universe. It challenges us to let go of classical intuitions about locality, about emptiness, about cause and effect, and to replace them with a more nuanced, interconnected, and informational picture of reality. There is also a cultural and scientific benefit to this mode of inquiry. Ideas like QET and emergent spacetime, while speculative, inspire new generations of thinkers to explore beyond established boundaries. They open space for creativity, for interdisciplinary exploration, and for the kind of bold questioning that often leads to transformative insights. Some of these ideas may be wrong or incomplete, but history shows that even incorrect models can lead to valuable discoveries if they force us to look at problems from new angles. As we look ahead, the central challenge is not to find a definitive answer immediately, but to develop better questions. Questions that unite quantum field theory and cosmology, that guide experimental design, and that invite us to look at the universe not as a static machine, but as a living system of energy and information. Quantum energy teleportation, regardless of whether it is ultimately tied to dark energy, represents one such question. It reveals that our deepest assumptions about how energy moves, how information works, and how space behaves are still open to revision. It suggests that the vacuum is not the end of physics, but its beginning. A rich, dynamic substrate whose mysteries have only begun to unfold. In the coming years and decades, with new instruments in space, new laboratories on Earth, and new minds pushing the boundaries of theory, we may inch closer to understanding what dark energy truly is, and in doing so, deepen our grasp of the universe's most profound laws. Perhaps the force that is driving galaxies apart is not something added to the universe, but something already embedded in it, waiting to be revealed, not through matter or motion, but through the subtle architecture of the quantum world.